We will now continue our discussion of understanding and writing down the equations of motion of a system. When we started, we had very simple systems, and it was easy to do a force balance to understand what the equations of motion are. As things got more complicated, we started to use the Lagrange formulation in order to derive the equations of motion, but when we were done deriving those equations of motion, they looked a little bit complex. We want to be able to return to something that looks as simple as this. This is the so-called standard form. Not only is it a more concise representation of the equations of motion, but it also will provide some insight as to how or what the terms of the equations of motion mean. Here, we have a mass matrix, which is a square positive definite matrix that corresponds to the inertia terms of your equation. Then there's a Coriolis matrix, which correspond to the velocity and moving rotational frame issues of your system. And then finally, there's a gravity vector, which captures all the potential energy terms of your system. Of course, all of these will be equal to your input torques that we were able to derive when doing our formulation. Let's return to our example of a 2 degree of freedom system where we have a rotational degree of freedom here and a translational degree of freedom on the second rigid body. Here are the centers of mass, and the generalized coordinates are labeled as such. Recall that the equations of motion that we derived using the Lagrangian formulation has this form, and even for a simple 2 degree of freedom system, the form becomes a little bit unwieldy. However, what we're able to do now is start to group our terms. So the mass matrix is in front of the acceleration terms, and what we can do is group all of the terms that are associated with acceleration terms into this matrix, the mass matrix. The Coriolis matrix is associated with the velocity terms, and likewise we can group our velocity term, the terms associated with our velocities, q1 dot, q2 dot, and so forth. And then finally, what's left over are the potential energy terms that we have in the gravity vector. So now we can write the equations of motion in this nice compact form where we can also get some intuition. The mass matrix, the terms in front of the acceleration terms, is this square positive definite matrix. Just as a reminder, a positive definite matrix is sort of a generalization of what a positive scalar can be. We would expect mass to be a positive number, and therefore a matrix is positive definite if for any vector v transpose mv is going to be greater than 0. If you look at this a little carefully, this looks like a kinetic energy term. And it shouldn't surprise you that kinetic energy is always going to be positive. In other words, the m inside of the kinetic energy has to be this positive definite matrix. We're going to discuss the Coriolis terms in the next lecture, and of course the gravity, the potential energy terms are fairly self-evident. However, the result is this nice compact explanation of what the physical meaning of the equations of motion are. What I want to do is spend a little bit of time talking about the Coriolis and centrifugal forces, because sometimes this can be confusing at first. So let's consider this example. Of a turntable that's moving counterclockwise, there's a ball here, and it's pushed straight towards this red dot. If you're standing on top of the table away looking down, you'll see this ball move in a straight line, and the red dot, of course, will move to the 3 o'clock position because it's rotating counterclockwise. Now, let's pretend you're standing at the point from which the ball was initially launched. From your perspective, you're going to still be looking at the red dot, but the ball is going to veer to the right. This is consistent with what the observer from above had. However, from your perspective, in order for this ball to veer to the right, there had to have been some sort of force, a fictitious force. That's the Coriolis force. The centripetal force is a little bit easier to understand. Anybody who's taken a string with a ball at the end and whipped it around real fast could feel the centripetal force. That's the force that's pulling the ball in so it can stay on the circular orbit. The centrifugal force, that's the reactive force. That's the force the ball feels when it's going around in this orbit. So if you've been in a car and all of a sudden you make a sharp turn, that force you feel that pulls you out, that's the centrifugal force. So now let's see the centrifugal and the Coriolis forces working together. Let's put you on a turntable that's rotating clockwise, and let's denote positions 1, 2, 3, 4, 5 as such. At position 1, you're holding a ball and you just let it go. Now, because the ball was already in motion, it's going to move along the tangent of the circle from the point from which you let go. From an observer who's standing on top of this system, the ball moves like it's in a straight line. And we've noted equal time steps along that straight line. You're still on the turntable. From your perspective, the ball is both moving out and deflecting at the same time. The contribution of moving out is the centrifugal force, and the contribution of lateral motion because of this rotation, that's the Coriolis force. So if you want to see where the Coriolis and centrifugal terms are encoded inside this Coriolis matrix, what we do is we introduce this other term here. It's called the Christoffel symbol. It actually has 3 indices, I for the ith generalized coordinate, and then jk, where if j is equal to k, it's a centrifugal force, and if j is not equal to k, it's a Coriolis force. So in this case here, when j is equal to k, what we're seeing is the contribution that the prismatic joint has to apply to the system in order to resist the centrifugal force from the mass of the second body being thrown out. When j is not equal to k, this is the Coriolis term. What you're seeing here is the torque that the revolute joint has to apply in order to keep the system rotating at a constant angular velocity. Now, at this level of detail is more for your informational purposes. We're not going to expect you to be able to derive these symbols, but we wanted you to know that there are centrifugal and Coriolis force terms encoded into the Coriolis matrix.